Now we're going to go into imaginary and complex numbers. Negative numbers were created from the need to do subtraction. And the imaginary number, j equal to the square root of minus 1, was created from the need to take the square root of negative numbers. Mathematicians use the letter I. We use j to avoid confusion with current, which is denoted by I. Since the square root of minus 1 does not fit on the real number line, a complex plane was created to give it a space. And we'll be showing that here. Now, where was I? Oh yeah, here we are. So look at this number line, which does not contain any negative numbers, and tell me, what is 3 minus 7?
Is that a trick question? I can start at 3, but I can't go 7. There are no negative numbers.
That's right. This number line is insufficient to provide an answer. So let's extend the number line to include negative numbers. Now, what is 3 minus 7?
Oh, negative 4.
Right. And the square root of minus 4?
All right, now I get where you're going with this. So that number line is insufficient to provide the answer.
Right. I will show you another method that does not violate your intuition. Mathematicians created the complex plane, which has the usual real numbers on the horizontal axis. These are the real numbers, the horizontal axis. Imaginary numbers are placed on the vertical axis. We have plus j and minus j on the vertical axis. And since j squared equals minus 1, by definition, then the square root of minus 4 is the square root of 4 times minus 1, which is the square root of 4 times j squared, which is easy to take the square root of. It's just 2j. It's a purely imaginary number, so it fits on the vertical axis. So 2j would be right here, 2 up on the vertical axis. A complex number has a real part and an imaginary part, such as the point minus 2 plus 4j, shown in the figures. You have minus 2 plus 4j, and you end up with this point here. Now we're going to look at why imaginary numbers produce solutions to real-life engineering problems. Have you ever felt uncomfortable that the imaginary number, the square root of minus 1, which is used everywhere in engineering, produces real-life engineering solutions? I will show that the imaginary number j is not imaginary at all. We just call it that. I have created a model called the j-plane that provides an alternative viewpoint for understanding imaginary numbers so it doesn't break your intuition. You'll not find this explanation anywhere else. I will show that the problems with the minus number line itself will no longer treat imaginary numbers as snakes that you have to deal with carefully. We were raised with the real number system, and it is hard to imagine that there's anything inadequate with it. But the definition of j is not intuitive and has created anguish among students and engineers alike. For how can an imaginary number that can't even be imagined produce real-life solutions to engineering problems? I said the problem is based on the definition of the negative number line itself. Negative numbers are great for balancing your checkbook, but poorly model natural processes because there's no place for the square root of minus 1 on the real number line. The complex plane, that's this thing here, which consists of real numbers on the horizontal axis, and imaginary numbers on the vertical axis, was created to solve the problem, but it fits like a 5-legged cow. So here we have negative numbers and positive numbers, but imaginary numbers kind of don't really fit. It works, but at the expense of breaking one's intuition since it can't be imagined. On the complex plane, if a number falls on the horizontal axis, it feels right, and it is real. Everywhere else, it has an imaginary component to be treated carefully like a snake. We start with a redefinition of the number line that is designed to allow taking square roots. In this model, the minus number line is replaced by the j squared j squared number line. It looks like this. So you have your regular positive numbers, 0 to 5, and then you go negative, j squared 1, j squared 2, all the way through j squared 5 and on down. Why can we do this? Because it's useful. The negative number line, being a creation of man's mind, is not sacred. Now, with this number line, can you compute 3 minus 7?
Yeah. I can start at 3, move 7 places to the left, and end up at j squared 4. Its square root is easy, just 2j.
Right. It's the same result as traditional complex numbers, but now we have another problem. There's no place to put j2 on this number line.
Oh, yeah.
So we resort to the j-plane, a more natural conceptualization of the complex plane, which produces the same results without resort to square root of -1, and suggests that there really is no possible operation going on. The fact that imaginary numbers do produce real-life solutions proves the reality that nature doesn't care whether you're on the left or right-hand side of 0. You can take the square root of either. You can see here that we have the same point we had previously with minus 2 plus 4j, but now it's, instead of minus 2, it's plus 2j squared, since we're using the j squared number line. 2j squared plus 4j gives us this point here. Mathematics represents and models nature, and nature doesn't care what you call it or how you represent it. All that is necessary is that you take the square root when it is called for. It is no longer necessary to perform an imaginary operation, and the mystery why imaginary numbers produce solutions to real-life problems vanishes. The I-plane has a symmetry, harmony, and beauty that suggests a deeper link to nature than the complex plane. Instead of 2 axes, real and imaginary, there are 4. J to the 0, that's the positive real axis, j to the first, j squared, and j cubed. Each is a power of j whose use removes the necessity of breaking one's intuition. There are no negative numbers, and all 4 axes increase as one moves away from the origin. Without a negative, it is not possible to take the square root of a negative. But j squared still equals -1 if you want to convert to the complex plane. Here's why imaginary numbers are so important in engineering. The voltage in a capacitor lags the current by 90 degrees, and the current in an inductor lags the voltage by 90 degrees. Whenever you multiply a vector by j, for example, 4j plus 2j squared, shown in the j-plane, the vector rotates counterclockwise by 90 degrees. So we've multiplied this 4j plus 2j squared by j. That gets you here, which is 4j squared plus 2j cubed. 4j squared plus 2j cubed gives you this point. So multiplying by j rotates 90, and multiplying j again rotates another 90, which is 180 degrees. Every time you multiply by j, you rotate the vector counterclockwise 90 degrees. Do this twice, and you have multiplied by -1.
Ah.
Yeah, isn't that amazing?
Yeah.
This is why j squared equals -1.
You should patent this. Yeah.
At least publish it.
Yeah, absolutely.
The reason why j produces real-life engineering solutions is because resistance, capacitance, and inductance are the most fundamental quantities in electronics, and when defined in terms of j, the 90-degree relationship between voltage and current, the impedance Z equal to V divided by I, is accounted for in the equation. So here's the impedance of a resistor. It's just plain old R. Okay. For capacitor, it's 1 over j omega c, which is minus j over omega c. They're equivalent. 2 different forms of looking at it. And the inductor is j omega L. As a bonus, using these values when solving a network equation removes the need for calculus, but it only works for sinusoids. But what exactly is j? It's just an axis with different powers of j used to represent real numbers and their square roots, without breaking one's intuition. There really is nothing mysterious going on at all in this model. And since everyone uses the complex plane, you should also. Only now you know there is nothing imaginary going on. We just call them imaginary.